Hey everyone, welcome to today's lab briefing. As your lead engineer, I'm kind of pulling back the curtain today for a bit of a reality check. We're going to dive into just how fragile standard microcontroller boards can be, and more importantly, how we can actually engineer our projects for true hardware longevity. Think about it like this. If you try to drive a massive semi-trailer absolutely loaded with gold bars over some rickety little country bridge, well, you're going to exceed the weight limit and completely destroy that bridge, right? And it's not the bridge's fault. It just has limits. Our hardware is exactly the same way. Ignoring those limits, that's a one-way ticket to catastrophic failure. So here's our game plan for today's explainer. We're going to hit the engineer's reality check, look at current limits and catastrophes, tackle overvoltage and reverse polarity, compare standard versus industrial grade, walk through diagnosing a dead board, and finally wrap up with engineering for longevity. Let's get to it. Section 1, the engineer's reality check. This is where we establish our baseline and set some proper expectations before we wire up a single component. Out in the field, you're almost always going to start prototyping with standard dev boards, like the classic Arduino Uno R3. It's a fantastic tool, really, packing that 18-mega 328p processor. But here's the hard truth. While it's great for learning, it's actually incredibly vulnerable to basic operating mistakes. I mean, it is absolutely not invincible. So, the most crucial concept you need to grasp today is what we call absolute maximum ratings. Basically, this is the strict threshold explicitly listed in a component's datasheet. Cross that line, the manufacturer literally waves their hands and says, "We no longer guarantee this chip won't be fried." Exceeding these limits is exactly how you turn a brand new microcontroller into a useless paperweight, like within 5 minutes of unboxing it. Moving on to Section 2, current limits and catastrophes. Honestly, this right here is where the vast majority of engineers fry their very first board. All right, the magic number you need to sear into your brain is 40 milliamps. The datasheet specifically caps direct current at 40 milliamps per input/output pin. And as a hard and fast rule for hardware longevity, you never, ever want to operate right at that absolute maximum. You've got to design your circuits to stay comfortably below that line, ideally staying under 35 milliamps. Let's walk through exactly what happens when things go wrong. Step 1, you set an I/O pin high, outputting 5 volts. Okay, cool. But step 2, you accidentally brush a jumper wire from that pin straight to a ground connection on your breadboard. Oops. Step 3, Ohm's law instantly takes the wheel. Because there's an internal pin resistance of just 25 ohms, pushing 5 volts straight to ground forces a whopping 200 milliamps through that circuit. And step 4, well, that's 5 times the absolute limit. That internal pin trace is instantly, permanently destroyed. But wait, here's the real kicker with that 200 milliamp number we just calculated. It isn't just a threat to that one single shorted pin. No, 200 milliamps is actually the absolute maximum current rating for the entire microcontroller combined. The whole shebang. And it is shockingly easy to accidentally hit that total limit. Think about it. If you've got just 10 standard LEDs, each drawing 20 milliamps, and they're all hooked up to your digital and analog pins running at the same time, boom, you're drawing exactly 200 milliamps. You have completely maxed out the chip's capacity. Add even one more tiny sensor to that load, and you're risking burning out the core processor. Okay, Section 3, overvoltage and reverse polarity. Because if you thought current limits were unforgiving, voltage limits can be way more destructive if you get sloppy with your power supplies. Let's talk about the classic, fatal mistakes you absolutely have to avoid in the lab. First, applying more than 5.5 volts to any standard I/O pin, that'll fry it. Hitting the reset pin with more than 13 volts, that destroys the microcontroller entirely. Sending more than 3.3 volts to the dedicated 3.3V pin will just blow its regulator. But the absolute most common mistake we see? Simply wiring a 9-volt battery backwards into the VIN and ground headers. Reversing that polarity is an instant death sentence for the board. And this right here really makes the case for careful power management. Let's say you decide to ignore the manufacturer's advice and apply 5 volts externally, straight to the 5E pin, while simultaneously hooking up a load to the VIN pin. Well, you've just created a fatal loop. You're literally forcing current backward through the board's 5-volt voltage regulator. And yeah, that destroys it completely. Section 4, standard versus industrial grade. So how do we actually protect our projects from these, very human errors? Well, as engineers, we look at how the pros do it, how rugged industrial alternatives build their armor. Let's compare overcurrent handling. On a standard board, like we saw, a short to ground instantly vaporizes the internal pin trace. But when we look at industrial boards, like the Arduino for example, they actually build in these 30 milliamp resettable PTC fuses in series with every single I/O pin. Meaning, if you short it, the fuse trips and safely cuts off the current. Remove the short and it resets itself. It is literally designed to actively prevent you from destroying it. And that same professional philosophy applies to voltage and polarity mishaps too. Reversing polarity on a standard board, catastrophic failure of the regulator and microcontroller. But rugged boards, they use blocking diodes and voltage cutoff circuits. They can actually tank up to 30 volts of accidental misuse. They just automatically disconnect the circuits before the hardware even feels a thing. Now, Section 5, diagnosing a dead board. Because let's say you're using standard hardware, you made a mistake, and the worst has happened. Nothing's responding. Here is your lead engineer's triage guide. First up on your checklist, plug it into USB and check if that green power LED lights up. If it's totally dark, you're dealing with a power delivery failure. Second, look for the factory programmed blink on the pin 13 LED. The bootloader pulses this, so if you see that blink, good news, the main chip is actually running. But finally, if the USB bridge is fried, you're going to have to bypass it and try to talk to the chip directly. So if that USB interface is completely toast, you can jump over to the 6-pin ISCP header sitting right next to the main processor. By hooking up an external programmer directly to that header and running some software like AVRDude, you can query the device signature. That tells you definitively whether or not the main chip itself survived the disaster. All right, final section, number 6, engineering for hardware longevity. Let's wrap this up by establishing the core mindset of a truly successful hardware engineer. It really boils down to this. Strictly adhering to datasheet specifications and operating conditions is the absolute hallmark of a professional engineer. Proactive engineering doesn't mean just crossing your fingers. It means calculating your loads using Ohm's law, meticulously using your current limiting resistors, and respecting those absolute maximum limits from the very first day of your build. So, as you pack up and head back to your workbenches to tackle your next prototype, I want to leave you with one absolutely crucial question to chew on. Are your standalone projects built to survive the real world? Think about your safeguards, double-check those data sheets, and always, always engineer for longevity. Thanks for joining today's Explainer, guys, and I'll see you next time in the lab.